if we use the fundamental theorem for velocity, they may ask you to actually calculate the particle's displacement or the object's displacement. Then you would simply integrate the velocity. So integrating velocity gives you displacement. That will be a test question, I'm pretty confident. The other two ways you get tested using the fundamental theorem is they'll expect you to know how to rearrange the theorem to deduce the location of the particle at some time. The rearrangement is very simple, and the idea is simple. You have an object. The object's moving. They perhaps tell you that I'm just going to make it, well, we remember from earlier, they tell you something like, oh, the position of the particle at time 0 is 10. So you know the particle is here when time is equal to 0. And then you know that when you integrate velocity, you're finding displacement. Please remember, displacement does not tell you how the particle moved. It just tells you the final result. So we figured out previously that an estimate for this integral, let's go back here. So we figured out an estimate for this integral, item C, was 234 miles. 234 miles is the plane's displacement, at least an estimate of the displacement, for the 40-minute time period. So the idea is very simple. If I know the plane was at location 10, and I know the displacement for the next 40 minutes, I know the particle displaced 234 miles to the right. So now I know the new position. I know right here, this would be position 244, and this would be time equal 40. That's all this version of the fundamental theorem is telling you. That's all that's telling you. Questions? Give me one or two if you feel comfortable with the idea. Show me. Go ahead,
So
please.
just to clarify, it's basically just what we've been learning. Like the
Yeah,
whole-
nothing new. Just kind of backing up a little bit as we go forward. So, show me one or two. 2 points for the root. Okay. Item A says to rearrange the fundamental theorem to create an equation which can be used to calculate the position of the plane at time equals 0. Well, I want the position at time 0. Please remember, this entire symbol contains a whole bunch of information. It tells you where the plane is located at a specific time. So that orange box means where the plane is at time 0, which in this example would be location 10. So the S of 0 is 10. If we don't know that S of 0 is 10, but we happen to know that S of 40 is 244, we just have to take away the displacement. So now you're subtracting. You're just going backwards. You're saying, oh, well, at time 40, I know the plane ended up at 244, location 244. The displacement for the period was 234 miles, so I've got to take away that displacement. Now I'll know the new, I'll know where the plane was, which was location 10. You're just doing it backwards. Show me one or two if that feels okay. If it doesn't feel okay, show me two. So we can keep finding new ways to talk about it. Points for the room. Talk to me, Kevin.
Sorry, I was just writing down everything, and you're just basically rearranging it to find what the displacement is, which is 10.
Well,
Yeah.
okay, let me just say it back to you. So again, I think I mentioned this last time. On a typical AP test, there will be about 1/3 of all problems will not be able to be solved unless you understand the fundamental theorem. The three most common ways they test you of your knowledge of the fundamental theorem are: just do an integral and understand what the integral is computing. So in this case, understanding the integral's computation is very simple. You just look at the symbols. We're taking velocity, so let's make up a velocity here, I don't know, 9.5 or something, miles per minute. Come on. And you're multiplying by a duration of time. So we'll just say 10 minutes. Well, the minutes divide out. You're left with 95 miles. So one thing they're going to test you on is, do you understand what's really happening when you integrate? And in this case, we're just finding a displacement. So that's one thing you get tested on, is just that idea, finding displacement or something similar. Questions? Please.
Can we look at integrals with acceleration?
With what? So Kayla's question was, will we ever do an integral that uses acceleration? Here's an example. If I'm integrating the acceleration over some time period, all I'm essentially doing is taking an acceleration value, I'll just make one up here, 25 meters per second every second. That's a value of acceleration. I will be multiplying that acceleration by some duration of time. So we'll make the math easy here. We'll say 4 seconds. So the seconds divide out. I'm left with 100 meters per second. Okay, acceleration tells you how rapidly the velocity is changing. So what this computation is assuming is that for the entire 4 seconds, the velocity will change by 25 meters per second every time 1 second of time elapses. So if 4 seconds of time elapse, my velocity is going to change by a total of 100 meters per second. So it's calculating how much the velocity changes. Just like this integral calculated how much the position changed. So when you integrate velocity, you calculate how much the position changes. We call that displacement. When you integrate acceleration, we calculate how much the velocity changes. That just doesn't have its own name. It's just how much the velocity changed during that time period. So we will do that as well. That's another way you get tested on that idea of the fundamental theorem. So show me one or two, if you're reasonably comfortable with the idea that you'll get tested on this portion of the fundamental theorem. Show me one or two. If you're comfortable with that idea, that you just look at what's, just like look at the symbols. Just write them down. Velocity multiplied by duration of time gives me displacement. That's one element of the fundamental theorem. One or two again. Show me, I gotta know. If you don't know, just tell me two. Okay, 2 points. Then all we did here was we said, well, there's no reason we can't rearrange these three symbols. Like, think of it this way. The fundamental theorem is no more complicated than A is equal to B minus C. And if instead of wanting to compute A, you want to compute like where the particle ends up being at time 40, you're just rearranging to solve for this. Because we're looking for the B right here. So if I rearrange to solve for B, all I do is move the C across. I end up with C plus A is equal to B. That's what this equation is saying. And then in common sense terms, it's even easier because it's just saying, well, if you want to know where the particle ended up, you need to know where the particle was at the beginning of the time period. The particle was at location 10 at the beginning of the time period. The integral tells me the displacement's 234. So that means the particle is now 234 more to the right than where it was. So now it's got to be at 244. The math that gives me that result is simply this blue formula. To be honest, show me 1 or 2 if that feels good. 1 or 2 on the blue. Sometimes if I stay there, don't move. Sometimes if I just act it out, it helps. Look, here I am, times 0, I'm at 10. 40 minutes go by. I've got to be 234 that way. So when I go 234 more that way, I'm now at 244. That's all this equation is telling you. We want to talk about it. This one is simply the reverse. Instead of solving for B, we ended up solving for C. Okay, we just solved for C. So to solve for C, move the C over, then move the A back over. You end up with C equals B subtract A. It's right here. This is the B subtract the A. Just taking it back out. So, questions? Okay, you'll be tested on all 3. We'll practice in the packet. Did we talk about a right Riemann sum in this class?
Yes.
Got some this way, some this way. We'll do it together. Okay. Yeah, show me 1 or 2 if you feel comfortable with the left Riemann sum. 1 or 2, are you comfortable with our previous discussions of left Riemann sum? Talk to me, Cameron.
I just kind of forgot what that was.
So we'll do a right, and then I think we'll trigger the memory of the left, to be honest. 2 points for everyone for voting. Okay, we're supposed to do a right Riemann sum of this integral. Look at me. Don't memorize the manipulation. Like, that's what gets people in trouble prior to calculus. They don't learn the ideas, they just learn the manipulation. Like, learn the idea, then you won't forget. We're doing this integral. The symbol is going to tell us exactly what to do. Okay, we're trying to take velocity multiplied by duration of time. How do we do that? Well, we're supposed to do it for the time period from 20 to 35, in this case, minutes. So I'm going to mark that off. 20 to 35 minutes. It says do it with a right Riemann sum, 3 subintervals of equal length. So the first subinterval goes from 20 to 25, second 25 to 30, third 30 to 35. Show me 1 or 2 if you feel good about how to break up the subintervals as described in the problem. 1 or 2. 2 points for the room. Okay. All that's left to do now is take velocity multiplied by duration of time. But we're supposed to do it 3 times. Please remember, test 4 is written, no multiple choice. However, much like the multiple choice tests, there are basically 25 things you have to answer. The difference is it's all written, so it's like 25 key items you've got to get right. One of those key items is often writing an integral. So on the next test, if you forget to write the integral, your score drops from 100 to 97. Like, you have to write the integral.
It sounds like you have to do that for each section, you just have to do it the first one.
When they say include correct units, you only have to have the final result with units.
Oh, okay.
Yeah, 2 points. You don't have to have the units along the way.
Okay.
Sometimes I'll write the units along the way just to verify that I'm not making a mistake, but you don't have to. Okay. I've got to have 3 computations of velocity multiplied by duration of time. So I look at my subinterval and I pick the velocity that is most right within the subinterval. So in the first subinterval, the velocity that is most right is 2.4. So that's the velocity I write down. And as I said to Kayla, 2 more for her. If I write some units here, it might help me make sure I don't make a mistake. So miles per minute. That gets multiplied by a duration of time. 5 minutes. And now I know my thinking is working because I'm not just blindly doing steps, I'm thinking about what I'm doing. 1 second. 2.4 miles per minute means every time 1 minute elapses, the plane moves 2.4 miles to the right. Well, if I do that 5 times, I'm going to know the total displacement for the 5 minutes. So everything's making sense. I'm feeling good about my computation. Thomas, please.
I'm sorry, I was just going to ask about the integral equation, like for the actual integral. Will those variables like dt times dt always be the same on an integral, or will it ever be different in the future?
No, good question. So we're starting out integrating only velocity, but we will do numerous examples of integrating all kinds of stuff.
Okay.
Yep. 2 points. Somebody else? All right, so I just continue. I go to the next subinterval. Please raise your hand if you know what I write next. I'll pay everybody for this one. What gets written next? Show me your hand. What gets written next? Melissa?
2.4 miles times 5 minutes.
So she goes to the next subinterval. The velocity that is most right in that second subinterval is right here, 2.4. My duration of time for that subinterval is still 5. How many knew it before she said it? Show me. Points 3 from Melissa. Question. Whoa. Last term, hands up. What's the last one? Show me. What's the last one? Savannah? 4.3, the duration of that subinterval is still 5. We'll cheat and just use the answer key there. Questions? 3 for Savannah, 2 for everyone else. Please.
When we're doing the integration on the written portion, do we have to include the units of like miles per minute, or can we just do it like the second and third examples where you have
Gotcha.
times 5?
These units are not required to get points. They're just me kind of checking, make sure I'm not making a mistake. These units are required. So this would be another example of if this problem were worth 3 total points, on the test I give you, that would be 9 points, because we're doing it out of 100. And if you forget to write the integral and you forget to write the units, you suddenly just earned 1 of the 3 points. Like that's how it will be graded. So.
Like, as if you have problems that start, like, don't say equal length and it's just like 3, and so then you have to make subintervals that are like, one of them might be 5, and then one of them might be 6 minutes, and the other might be 7.
Yeah, Kayla's question was, are there going to be problems where the subinterval lengths won't be uniform? They won't always be 5. You'll encounter some problems in the packet that are like that. It's not any more difficult. You simply follow whatever instructions they give you. So for example, this one, there we go, hold on. Right there. They tell you that they want these subintervals. So no longer are the subintervals equal, but no big deal. You just use whatever subintervals they tell you.
Will they ever like not tell you when you say break down the grade and just
Yeah, like the next one I'm going to show is like, so then Kayla's next question was, so she understood that, hey, here they're specifying what the subintervals should be. I just follow those instructions. Here's an example in the packet that you'll do as homework where they say, right here, Kayla, do 3 subintervals as indicated by the data in the table. So you just follow the table.
Okay.
They're saying do an integral from 20 to 40. come up here. We start at 20. We end at 40. And we need 3 subintervals as indicated in the table. So that means here's my first subinterval, turns out to be 5 seconds long. Second subinterval turns out to be 7 seconds long. Third subinterval turns out to be 8. Is that your question?
Yeah,
Please.
If they're unequal intervals, do you still integrate them the same way as you would if they were equal?
Yeah, you're still just following the symbol. The symbol says, so Luke's question was, is the integration changed? Not as long as you're following the principle, the concept, because the integral says take velocity multiplied by some duration of time. Well, for the first subinterval, we're going to pick a velocity and multiply by however long that subinterval is. So this integral is going to have something times 5, then something times 7, then something times 8. Is that your question?
Yeah.
3 points. Please.
Are they ever gonna give us a problem where they don't tell us how many subintervals they want?
Cannot recall that ever happening. So Zach's question was, did they ever give us a problem where they don't tell us how many subintervals? I don't have any recollection of that. Well, they could do it here, I suppose. Like, they could have said this, Zach. It would not have caused you any trouble. They could say, hey, do the integral from 20 to 40, d of t dt. Leave this off and just say use subintervals as indicated by the data in the table.
Oh, yeah. Okay.
And you go, oh, I got it. I'm supposed to go for 5 minutes, 5 seconds, 7 seconds, 8 seconds, because I'm just following the table.
Oh, okay, cool.
They may have done that. Does that make sense?
Yeah, that makes sense.
3 points. Please.
Or could you just re-go over how you would use a trapezoidal Riemann sum in this situation with 2? I just kind of forgot the definition of a trapezoidal.
You're good. We actually haven't talked about trapezoidal yet, so we'll hold on that one for a little bit. No worries. We'll get there together. So that's why your memory's kind of going, wait a minute, I don't think that seems familiar. It's because we haven't actually talked about it. Okay, back to here. There we go. Okay, show me 1 or 2 if the right Riemann sum feels comfortable. Show me 1 or 2 if the right Riemann sum feels comfortable. Okay, 2 points for the root. Okay. It says use the graph to illustrate what the right Riemann sum would look like. Again, it's as simple as just thinking about what you did. Oh, yeah, please.
How many places after the decimal should
Say it one more time.
How many places after the decimal should you like
Oh, gotcha. Kayla asked for how many decimal points. If you punch it out on your calculator, it comes out perfect, like this, where there's really no additional decimal places. You can just show what's perfect. If you end up having to round, you always round to 3. Okay, item C is not hard as long as you simply follow what you just did. We took 24.4, so we're over here at this time interval 20 to 25. 24.4 is the value of the velocity on the right side of the time interval. So we're taking that length, we are multiplying by a time period of 5 minutes. So the width of our computation is this much. That means we're finding the area of this rectangle. That's what our computation looks like on the graph. Okay, all we did was take the height of the rectangle multiplied by the width. So we're finding the area of that rectangle. 1 or 2 if that makes sense. Show me. points for the room. Talk to me, kid.
When I get the, I just don't understand like how the graph translates into.
So you're, let me see if I can kind of think what you're thinking. You're okay that, hey, I've got written down that I'm supposed to take 2.4 times 5.
Yeah.
And 2.4 times 5 is, definitely the height of this rectangle multiplied by the width.
Yeah.
So you see that.
Yeah.
The reason we draw it on the board is to make a comparison.
Okay.
We're talking about a 5-minute time period. In those 5 minutes, is the velocity always 2.4? No, we've talked about that a lot. Velocity is different over the entire time period. If we had done the computation more accurately, we would have wanted to sample or check the velocity more often. So let's say we do it every 1 minute. Well, what would happen then is we'd get rectangles that would look like this. We would check the velocity at time 20. The velocity would be this value because the graph tells me that's the value. The width of my rectangle, though, would be quite narrow because I'd only be multiplying by 1 minute. So I'd get kind of a rectangle that looks like that brown one.
Yeah.
Then I would go to the next minute and find a new velocity that would look something like this. I multiply that by the 1 minute. I'd get a rectangular area about like that. Does that make sense? The idea is that if I keep doing that, I'm going to pretty much fill this space with rectangles. And that would be the perfect situation where we check the velocity enough that the area we're creating by doing these computations is going to fill all the space between the curve and the horizontal axis. Our estimate only filled that much space, so we know that we're estimating too low. That's the idea of drawing it out.
Yeah.
Comments?
Do they ever use an example where, like, instead of using just a right Riemann sum or like a left one, they use whichever one is more accurate? Like on this graph over here, for this one, the left one would be more accurate, maybe, or maybe even like another type of Riemann sum. And then as we get closer to that, relative minimum there, once we get past that, then you use like a right Riemann sum.
Gotcha. For our class, they've never tested to that level of detail. They are primarily wanting to make sure you understand how to find a right or left Riemann sum. And then they do want you to be able to recognize, like I just talked with Kayla about, and what you also recognized is to, is my Riemann sum approximation too high or too low? They will ask that sort of thing, but not quite as complex as you were describing. So.
Okay.
Good point. Question. And then you just keep doing it. So like the first computation looks like this. So we're 5 wide, 2.4 high. That's my first computation. The second one's right here, same thing. Third one's over here. Like that. Question. Cool. Guess we've done all that. Go to page 4, please. Okay, A and B are not new ideas, so I'm going to leave those for homework. So A and B are not new. You'll just do that in the homework. The next term we encounter is midpoint Riemann sum. I don't think finding a midpoint Riemann sum is going to be hard for you as long as you have understood the idea. So the thinking should be identical to left or right except for one small change. We still want 3 subintervals, still want equal length. We're approximating this integral, so we're going to write that down. So we write the integral from 5 to 35 v of t dt approximately equal to, we still go to our table and say we're starting at time 5, going to time 35, and we must have 3 equal subintervals. The table nicely accommodates that. We are still supposed to be multiplying a velocity by a duration of time for each subinterval. So please raise your hand if you know what's the first thing I should write on the board. Come on. Just think about it. Don't overthink it. We are supposed to do 3 computations. We're going to check the velocity 3 times. So we're going to go to the first subinterval. We're going to check the velocity. Where do we check it? At the midpoint. So Maddie, what's the first thing I write?
9.5.
So 9.5 is definitely the velocity that is in the middle of the first subinterval.
Oh, that's what that is.
What do I multiply by, Maddie?
10.
10, because the duration of the first subinterval is 10. So that's what I mean by, if you understand, like if you don't just memorize the manipulation, but you think about what you're doing, it's not hard to shift from left, right, or midpoint. How many knew it? Show me. 2 points, 3 for Matt. Questions, please, Ben.
So one thing I'm wondering is that, what's the difference between like, if you just, so I get that there's like how, why you would, how you would use midpoint, right, or left, but like, why do they do that? Like, why don't they give those 3 different options?
Gotcha. So, so Cameron's question is, why in the heck do we have a left, right, midpoint? It's kind of a little beyond the scope of this class, but it's not too big of a step. In a real life situation, you may want to use left, right, or midpoint depending on what the graph looks like that you're integrating. And so I believe that they're testing you on all 3 just to verify that you really understand the difference. That you're not just, again, memorizing the manipulation of symbols, but you're understanding the idea. That's all. So.
Would they ever ask us to do a midpoint sum where they don't give a specific midpoint type of problem?
Gotcha. Hold on to your question 1 second. Let's finish writing this out. Hands up. What's the next term? Somebody. Actually, everybody. What's the next term, Jacob?
4.5.
Times?
10.
Please raise your hand if you knew that before Jacob said it. 2 points, 3 for Jacob. Then just to finish make sure we're all good. Last one, hands up. Oh, that's the last one. It's for Melissa.
2.4.
Times?
10.
And we'll cheat again and just use the key over here. Item C, 164. Okay, how many knew it before Melissa said it? 2 points, 3 for Melissa. Andrew's question is, will they ever ask you to do a midpoint? It's kind of related to Zach's question of, how do I can't remember, I think it was Zach was talking about like the uneven intervals or whatever. No, they won't be unreasonable. So they would not ask you to do this, Andrea. Like if they said, find the integral from 5 to 20, they won't ask you to do a midpoint sum with 3 subintervals. Because the 3 subintervals would go here, and there clearly is no midpoint indicated for any of those subintervals. So they won't do that.
Okay, because it could be any.
Well, the midpoint's 7.5 minutes, but I don't have a good way to determine the velocity at 7.5 minutes. Does that make sense? 2 points. Please.
But if they gave you a graph, you could approximate it at that point in time, possibly, yes?
You could. I've never seen them ask that just because they don't seem to want to get into that whole problem of like, well, how good did you have to approximate that sort of thing? But you certainly could do it that way, yes. Yeah. Cool. I'll leave these 2 for homework. They're not anything new, so next thing. Go to page 5. 5 does not have any new ideas, so we're going to skip that. Let you do that at home. Six. Six also not really too much new. We're going to skip that for now. So go to 7. Okay, new idea here. This is one Thomas asked about earlier. Two more for Thomas. 7a says use the graph to illustrate what a trapezoidal Riemann sum would look like. We're integrating from 0 to 70. 0 to 70. We're supposed to do the subintervals as specified. So we're going to go from 0 to 20. Change color here. Then from 20 to 30. And then from 30 to 70. So far all I've done is follow the subintervals that they mention. Okay. It's called a trapezoidal Riemann sum because when you draw when you try to depict visually what the Riemann sum looks like, you end up with trapezoids instead of rectangles. The way you draw the trapezoid is you look at the subinterval. So we're going to go to the first subinterval. I pick the velocity that is most left in the subinterval. I indicate that. Then I pick the velocity that is most right in the subinterval, and I draw that. So now we have two heights for that subinterval. The most left velocity and the most right. You connect those two vertical lines with a straight line, hence creating a trapezoid. Like that. The formula we end up using is going to find the area of that trapezoid. So now you can see why most of the time we would consider the trapezoidal sum to be the best estimate. Because the area we are calculating is very close to the area that is between the curve and the horizontal axis. It's not very different. Questions? Please. Good question. It goes back to that. So Kayla's question was, why would you use the others then if this is most accurate? One big reason is when I go to, so that's what the trapezoidal sum is going to look like. Like if I keep going here, I can draw out the other two subintervals. They would look like this. And then the last one's over here. You should be able to see from this picture that this trapezoidal sum is going to be just a slight underestimate because the area of the trapezoids is going to be slightly less than the area would have been if we'd been able to follow the curve. Questions? Please, Jacob.
Are they always going to give us the trapezoidal? Are they always going to have us do the trapezoidal Riemann sum when they don't give us equal fragments?
Gotcha. 2 points for Jacob. He asked, will they always ask us to do a trapezoidal Riemann sum when the subintervals are of non-equal lengths? And the answer is no, that's just coincidence. Yeah, they just mix it up every year or something different. So we're going to get to Kayla's question in a second. So we've done these two. We show what it looks like. We can see that it's an underestimate. Anybody want to talk more about that? Okay.
Sorry, what does TRS mean?
Trapezoidal Riemann Sum. So good question. Points for Cameron. Okay, so going to item C, here's the answer to Kayla's question. We've got to do this Riemann sum, so we write the integral. You notice that in our drawing references two different velocities for a given subinterval. But remember the big idea. You've got to take a velocity for some subinterval. So what we do is we take the two velocities and we average them to create one. So to average two values, it's not hard. You just add those two values together. So I took the velocity that was most left in the subinterval, and I added that to the velocity that is most right in the subinterval. Once added together, I divide by 2 to get the average of those two velocities. This is now, remember, all we're doing when we integrate is we're just saying, hey, we've got to pick a velocity to represent a certain amount of time. So now we're picking two velocities to represent the first 20 minutes. So that's one reason why it's much more accurate, is because you're using twice as many velocities to do your check. We multiply that by the duration of time for the first subinterval, which is 20 minutes. That's how you do a trapezoidal Riemann sum. And one disadvantage is it's twice as many computations. So.
Why don't you just average out all of the work, like the work that gives us?
So Kayla's saying, why not make it even more accurate and average all three of the velocities within the subinterval? You certainly could do that, and there might even be a name for that. It's just not something we're tested on. Is that okay? Yeah, so nothing wrong with doing that. It's just not what they're asking. 2 points. Anybody else? So back to your question, Kayla. Left and right are just faster. They're just less accurate. So, cool. Please raise your hand, everyone. What's the next term? Hands up. What's the next thing I read? Let's go, Sophia.
So 1/2 times 22 plus 29 times 10.
So this is our subinterval. We pick the velocity that's most left, the velocity that's most right. We add them together. We average them to get a single velocity. We multiply by the duration of time. How many knew it before she said it? 2 points, 3 for Sophia. Please.
For the written portion, do we need to write it down like this, or would we just write down the already average velocity?
Gotcha. So Luke's question is, how much do we have to write for the written portion? I'd have to go back and check my notes to see what they require. For now, write it like this, please, even though I know it's a little bit tedious, just to make sure you're not forgetting what's really happening when you do a trapezoidal sum. Once we get closer to the actual test, I can check my notes, but I just don't remember. So. 2 points for Luke. Hands up, what's the last term? Hands up, what's the last term? Cameron?
1/2 times 29 plus 47. But yeah, parentheses 29 plus 47 times 40.
You knew it before he said it? 2 points, 3 for Cameron. Question? Cool. And that works out to be 2045. So. Okay, next one you can do on your own for homework. Going to page 8. Okay. We talked about earlier in the year, you need to have memorized. When the velocity is positive, the particle is moving right. When the velocity is negative, the particle is moving left. Go like this if you need me to say it again. Cool. Speeding up and slowing down. Velocity and speed are not the same thing, although they are extremely related. The speed is simply the velocity without a positive or negative. So the speed is just no positive or negative. It's just always positive. So notice here, the velocity is 3. Now the velocity is 4. Now the velocity is 5. That means the speed was 3, 4, 5. So just say the word up or down when I prompt you. for this blue portion of the velocity curve, is the particle speeding up or slowing down? Just say up or down. It's hard to say. That didn't really work out very well. Okay, the velocity went 3, 4, 5. That means the speed also went 3, 4, 5. So did I speed up or slow down?
Speed up.
There we go. Pretty good. Okay, we keep going, following the graph. The velocity here is 5. Now the velocity is going to be 4, 3, 2, 1, 0. That means the speed is going to be 5, 4, 3, 2, 1. Because when velocity is positive, velocity and speed are the same thing. So say it out loud, please. During the green portion of time, did the particles speed up or slow down? Say it.
Slow down.
Question. Cool. Now it's not trickier, you just have to pay closer attention. So now the velocity is 0, that means the particle is at rest. Now the velocity is -1, -3, -5, -7. So because the velocity is becoming more negative, the velocity is decreasing. Now the velocity is -10. But the speed was 0, 1, 3, 5, 7, 10. Speed was 1, 3, 5, 7, 10. Was the particle speeding up or slowing down? Say it. Speeding up. We want to talk about it, weigh that means. Cool. So during this time period, blue and green, the particle is moving to the right because the velocity is positive. During the blue portion, the particle is going faster and faster to the right. During the green portion, the particle is still going to the right. It's just slowing now as it moves to the right, eventually stopping at this time right here. Right here. Then during the pink, the particle is going left. It is going faster and faster to the left until we get to this time down here, which is time 20. The velocity is still negative. So, let's get this maroon, let's do bright green. Velocity is -10, then say -8, -6, -4. So negative means particle still going left, but as the particle is going left, the speed is going from 10 to 8 to 6 to 4 back to 0. So during the bright green, the particle is slowing. Should be 1 or 2 if that feels really good. 2 points for the roof. Okay. The rest of it's not new. I'll let you finish that at home. Okay, page 9, one item that causes people a little bit of trouble. Item C on page 9. The position of the particle at time 0 is 3 meters. So if I drew a picture, origin is always the location 0. It's not the original location, it's just location 0. It says at time 0, the particle is sitting here at 3. They want to know at time 8, is the particle moving away or towards the origin? So first of all, raise your hand and tell me, at time equal 8, is the particle moving left or right? Hands up. It's the graph of velocity. Time equal 8, about right there. Based on this graph of velocity, is the particle moving right or left? Come on, hands. That's it. The velocity at time 8 is said to be 5 meters per second. That means at time 8, the particle is definitely moving to the right. How many knew it? points 3 for Janessa. Stay with me, Janessa. From time 0 to time 8, was the particle always moving right, or was it going back and forth?
It was always moving right.
So from time 0 to time 8, the velocity of the particle was always positive, hence the particle was always moving to the right. So the particle started here, it's moving to the right, and for the next 8 seconds, it is still moving to the right. So that means at 8, the particle is moving away from the origin. Maybe 1 or 2 if that made sense. Talk to the camera. Points for the room.
So just one thing I'm confused with is like just, like, isn't it like decreasing right now, or is that just still like on the 8 right now? Is that just still going positive? Or
So,
increasing?
you're okay. Let me just ask you a series of questions, see if this helps. So, at time equals 0, is the particle on the right or left side of the origin?
On the right.
Does that feel good?
Mm-hmm.
Okay. From time 0 until time 8, is the velocity always positive, always negative, or kind of both?
Oh, it's positive.
So it's positive. So for those 8 seconds from time 0 to time 8, which way is the particle moving?
It's moving right.
It's moving right. Now it's moving right at different velocities. It's actually speeding up. Because the velocity went from 3 to 4, 3 to 4 to 5. Which means the speed went 3, 4, 5. This particle is speeding up as it goes right. But because this particle was starting on the right side of the origin, for the next 8 seconds, it's always moving away from the origin. Like it's getting further from here. I don't know if that helped you.
Okay. Yeah, that did help. And just to make sure I'm getting this, when it starts like decreasing and going to 0, that's like when it's starting to go back to the origin?
So right here is the velocity positive or negative?
Positive?
Positive. So which way is the particle moving?
Away?
Better to say right.
Oh yeah, right.
Which would still be away in this case. Sorry, slip. Right here the velocity is
Positive.
positive 3, so it's slowing down, but it's still going right. It's still going away. The particle will continue to move right and away from the origin until we get to here. Then the particle stops. Now the particle has a negative velocity, which means it's going back towards the origin. Any question? Please.
How much do you think A compressing us? Like, for instance, if they asked you instead, like, oh, is it speeding up or slowing down, and they, like, say it at 8, what would you say? Because, like, it's increasing the compress, like, after the first, and then it's missed it.
Oh, gotcha. Sorry, Kayla's question is, are they going to ask me whether the particle is slowing down or speeding up at this moment? Because that's the precise moment when the particle stops speeding up and starts slowing down. No, they won't ask it in the first question like that. So, question, like philosophy, like Ryan, please. What do you
Oh,
got?
I wanted you to continue for Cameron, and I could see where he was
Oh, perfect.
maybe wanting to see that other part.
Perfect. Okay.
Thank you.
The rest of it, nothing new. I'll let you do that at home. Okay, 10. 10 has a lot of words, but it's really not a complex idea. So I have the words for your notes, but if you can understand what I'm going to just talk about, you'll be fine. So I'll be the particle again. So look here, projector is the origin. I'm not starting there because origin doesn't mean where I start, it's just middle. So I'm starting at location 3. Don't overthink this. If I move 10 to the right, and then I move 10 back to the left, please raise your hand if you know what my displacement is for that time period. Don't overthink it. I move 10 to the right, I move 10 back to the left. What's my displacement for that time period? Jacob? Over here, Jake, sorry.
20.
So I'm going to help you understand the difference, no worries. I went 10 that way, right? 10 back. My total distance traveled is definitely 20. Because 10 left, 10 right, 10 left, total distance traveled is 20. Say it out loud, what's my displacement? 0. Does that make sense?
Yeah.
Oh, no, no, different.
Don't even worry. How many get it? Show me. Good. 2 points for the room. Good. 3 for Jacob. So, with displacement, it is critical that you keep track of positive and negative. So I had to keep track of 10 this way, 10 this way. So 10 to the right, 10 to the left, displacement of 0. For total distance traveled, I kind of like to just throw away the negatives. There? You guys want to go, oh, I went 10 and 10 more. That's why right here is the formula for calculating total distance traveled. It looks just like the formula for calculating displacement, except that the velocity has been absolute valued so that we don't count anything as negative. That's how you find total distance traveled. So when you do this kind of an integral in the homework, it's not harder. Just that instead of grabbing the velocities as given in the table, like this is a negative velocity, if you're finding total distance traveled, you just count that as 10, not negative 10. That's it. Questions? Please.
And will it just ask you, like, some problems will ask you to do like the displacement, and this will just ask you, like, clarify the total distance traveled?
Perfect. 2 more. Good work. I'll bring in 10 seconds.